A teaser clip video. This will show or talk about also the post-tension bars, why they're so critical. That NTSB, OSHA, Denny Pate, which we're looking at now, Denny Pate's forensic analysis guy, they all removed the post-tension bar out of the way of the shear plane capable of shearing off steel. Incidentally, the configuration is not as Denny Pate's engineers just set up. It's not on an angle like that. That it's approximately a 32 degrees column, if you will, the vertical, meaning a 90-degree column. So their testing is just nasty, false, misleading, BS, junk, and I find them to be lacking as engineers, and they shouldn't even have considered that. Their testing does not show two post-tension bars in place. I just find that just ridiculous, It's just stupid. It's just changing it to make it work. Hell, I'm trying to make everything fit, and for their system to fail, they have to remove everything. Now, Denny Pate says his system's redundant. I don't know about you guys, but it's getting pretty damn redundant to me. And that you saw I had no. This would just be like steel then. It's not concrete. It's not going to behave the same. But he's stating that the truss system, which he called the web, but then he calls it a truss system, is the redundant part of the system. I guess for semantics, he's going to refer to it as a truss, but I don't think he truly means it's a truss system. It's a web I-beam as it's been designed. So what I did now is I welded on the base. So now it has a base weld on it of the rough estimate of the profile. I did that on both ends, spinning around for you guys. I did that on both ends. Yeah, clarity, right? Sorry, this camera doesn't autofocus. Most expensive camera I have, and it doesn't autofocus. Well, that's the way cameras are. They don't autofocus. But you can pull in without changing focus. Without having to focus, which I'm doing right then. So now I'm going to load this again from the top. There is no bar. I didn't even add the bars yet across the bottom here. The only thing that's been giving it rigidity now, not this, it's not connected. So that's not connected. It's the diaphragms, the base, the pure caps. Watch the ability the structure still has before I add the post-tension bars to it, which I'll still add. But remember, I did the video, was it in number 4, where I show you see me stepping on it, and then in number 5 I cut it. Now you see the deflection is pretty intense down there. Let's do that. So down here it would be so much harder to get the same amount of force to make. I couldn't get the same amount of force to make this react. Now I brought back the clip to show you with just a little bit of force, and there's no weld, there's no connection to the diaphragm. It's just resting on top. Now watch my hand deflect, my hand pressure, and the deflection that takes place.
It's like that. See the deflection there?
So you see there's a big difference once I connect the diaphragm. Still stacking up for you guys. You got to bear with the video, the series.
Resisting. Now,
albeit the base is so critical here. This is what I'm going to add to you. See the base? I'm fully shimmed, if you will. I don't have it on top of 4 nuts, which I'll probably add 4 nuts to show you it's how shims will make it react differently. It's got a full base. The one to the left also does not have a full base, and the bridge is on an incline. So those shims would have to be identified as shim level, and because on an incline, that would change the pressure, how it relates to itself. Ignore that part where I lifted up. It's not really a true action, is it? So let me go ahead and step on it, and this is without the bars, which I'll add. This is with number 11 cut free, so number 11 is cut free. So this is cut free. Whoop. Did it tack weld in? No, I didn't even weld up there. Let me confirm something here. Okay, there we go. See, number 11 is free. Okay, what happened was I did step on it a little bit, and I created some deformation. Let's see what we got here. I didn't step on it much, but I did give it a little bit of pressure before the video start. I didn't do the full pressure, and I don't mind doing the full pressure, but let's see what happens. What's the reaction? I get myself a little safety grip here. If I fall down, I'll keep it on the video for you guys for clowns. Alright, so you see, I'm on it ×2, same way as yesterday, or 2 days ago. And you see there was some reaction out there. This is without the post-tensioning in the deck, which I will add. Let's do it again. So it does slide. Particularly, what's number 11 doing? The more we get this, the weight of this, the dead load, we only have a dead load causing a failure, guys. We don't have the weight of the pipes on this yet. So it's so simple to realize, okay, what are our loads? It's dead load. So why would the dead loads, why would this deck deflect? And I'm stating because of the span. Now this is steel, and it's going to react differently than your concrete, obviously. But it's giving her a scale +3/8, I told you. Plus +3/8. So -3/8. So the -1/4 to 3/8. So our reaction is the dead load of the structure only, the dead concrete load. That's all we have to figure out. Why did it deflect? And we have it because of forming. They said when they removed the forming that, let me see if I can give you a better lighting. Sorry about that. When they removed the formwork, cracks appeared immediately. The formwork was holding this thing together. The formwork was. Not the post-tensioning. Once it deflects after they remove the post-tensioning, after they remove the formwork, that shows you that, oh, we got the longitudinal post-tension cables. We got that calculation wrong. So when they remove the formwork, the bridge sagged. And right then, that's the death of it. That's the death of it. Sagging, it's going to continue its way down to hell. Now, the next video, I'm going to put bars on it. Post-tension single bar. And the thing is, I need 2 of them to keep it balanced. I can't run it down the middle. It doesn't exist. Theoretically, I could run it down the middle for you and I. Just say, imagine it was balanced. If I run a bar down the middle. I can't. The upright of number 12's in the way. So we'll have to jog it to the right of 12 or left of 12. And put it into the diaphragm of each one of the ends here. To show you what happens then. That if the bars were tensioned correctly or enough, that we'll get no deflection. So right now, I'll climb back up and you'll see some deflection. And when I put the bars in it, the right post-tensioning amount, if you will, then you'll see no deflection. So you're watching down here. I'm jerking on a little bit to get the reaction. All right, so I blocked a guy that I blocked some time ago. He came back and gave me 3 messages swearing up and down how 11 pushes off 12. That's just idiot engineering. If you have no logic, I wouldn't have you put together a loose leaf folder for me. So that's my attack back at anybody who's so effing stupid that can remove this bar in their formula. Can remove the bar in a formula. You're not stupid. You're just stuck on stupid. You're stuck on stupid because you have ACI saying you can remove the post-tension bar. The bars in this. That's just ridiculous. You have to defeat them. They're part of the structure. It's just ridiculous to even do an analysis without including every part. You can just So once again, I'm going to step back up onto the structure. I should also make you understand that this flat piece of metal without the weldment, without the connections, it deflects terribly. So don't think this is contributing that much by itself being flat. And the span I have it in, it deflects just as like nothing at all. It's 1/8 inch mild steel. And well, let's go ahead and show you that everything's free still. Well, I got a little binding there, so my deflection's kind of permanent. Some of my deflection's permanent. But I want you to watch the dip. Let me make sure my hands can be seen. Yeah, the dip in the deck here. And there, and it's Brucey in the background. Hey, Bruce. Okay, so he's attacking nothing. He's having a little fun. All right, here we go. What you got there, Bruce? Securing myself and going onto the structure. So what you hear, that popping noise in the background, that's the left bottom part of the diaphragm sliding, taking a new position, popping. I don't have it secured down here yet with the post-tension bars. Once we get those bars in there,
at that point.
we should not hear the
So
popping.
the longitudinal post-tension cables
Are just not working along with this system. The transverse tying in. So let me just theorize and throw it at you real quick. Let me change the ISO, meaning I'm going to increase the lighting a bit. And lock it down again. All right. Again, we have the data already that the collapse happened here and here, failure here and here, that this is no longer supporting because the cracks are evident. If it was supporting, we would see it shear off, and then the break should happen where? Where should the break happen? But it can't elongate because of the post-tension rods. Nobody shows that the rods were elongated, that they necked, they had necking in them, so they never experienced that force of turning these into a failed bar. Again, I'm asking NTSB for all the data, not just their narrative, so I don't know where that's going to go. You guys know government, NTSB specifically, has got an agenda. They're allowed to be lobbied. It's just BS. Nevertheless, your dead weight deflection, you see it doesn't make it even when I take this off. So when I take this off, because of the cracks are present, I'm able to show that the loads are really going down 9 now. Some of the canopy loads are coming back down 10 here, and some going down 12. But the loads are going down 9. So as you deflect, this dead load deflection of the deck is resolved in this nodal area here, again out to here. Number 11 has the split cracks in it. It's not compressive cracks. They're open, they have a torque, they have a rotation to it. That rotation to me is very critical considering it an I-beam. Is that you load an I-beam in the center, and finally when you get the failure, it's going to be that torsion that we see here indicated by the tape measure. Measure from the base of this, showing that it just obviously didn't fall down, straight down. It went up. And that's what the tape measuring, showing it's going up. The back side of it showing it's going up. Which I show in previous videos, I think even in this series, right? So that pulling up shows you that 9 went down. That 9 is lower than if you were to use a transit and take elevations. This elevation is lower than the elevation out there. That gives us our hinge, our elevation. All right, I'm going to stop this video. I've got the bar ready for you guys, just so you know. This will be in the next video where we now see if we can make this work redundantly with post-tensioning that will not give heave for the loads applied to it. Meaning it won't give to my fat arse when I put it on the one single bar. But for now, this is the data you're seeing, and we're going to get to it, the model.